So we will wait few minutes more to join others for the session. Am I audible to everyone? Can anyone confirm?
Yes, ma'am, you are audible.
Yeah, okay, thank you. Let's just start for the first session today. That is particulate solids. So about my introduction, I am Smita Mondal. I'm currently doing my PhD in Chemical Engineering Department of IIT Madras. I am continuing this live session of our NPTEL for this course, particularly as a part of my TA duty for PMRF Research Fellowship. So this starts to this session with the syllabus that we will be covering throughout the live sessions. First one will be the introduction of the particulate solids that today's class will be discussing on this topic. Next, the screening or the size analysis will be discussed, and then size reduction, different mediums or different equipment used for the size reduction. We will be discussing in detail, and storage conveying bulk solid, size enlargement methods, then flow past some mechanisms and the derivation will be covering in the flow past bodies. Then what is most important for any kind of okay, for any kind of flow through the packed and fluidized bed conditions. Then we'll be discussing on the filtrations and cross-filtration, gravity sedimentation process, centrifugal sedimentation, and flotation. So on these 12 topics we'll be covering over the live session. And then the first topic we're going to discuss in this live session, that is particulate solids. So moving onwards, we will be discussing about this little bit of background. First, the term unit operation that describes both physical and mechanical procedures that may occur parallel to the chemical reactions, which is known as unit process. It may be applicable for diverse material processing industries. So, if you visit any industry like ore processing industry, like coal processing, or suppose a different kind of mineral processing industries, so they are mechanical unit operations. This sector plays a very important role because before processing, before suppose you are extracting some metal out of some metal ore. So in the mineral ore, if you are going to extract the metal, then you need to crush it. You need to do some size analysis to get down that size from where your metal extraction can be processed, can be further processed, and we can extract the metal out of the ore. So, suppose the coal processing industry, which is very common for the chemical engineers, like many of us, we work in coal processing industries. So, which is a very vital source of fuel in today's generation or today's case. So, for coal processing also, we go lot of mechanical unit operations like flotation, froth flotation basically, then size reduction, size analysis, those kind of thing. We will one to one we will get through those topics in later stage. So, I would like to mention that what is the importance of the mechanical unit operation, that we are actually giving the interest to read and understand the knowledge behind the this particular topic. So these mechanical unit operations, while they are purely based on physical or mechanical forces like gravitational force, centrifugal force, mechanical and kinetic forces which arise from any kind of flow. So basically, mechanical unit operation that can be classified based on the phase interacting point of view. First one is solid-solid operation, where we can categorize it like involve crushing, grinding, sieving, compaction, cutting, storage, and transportation of the bulk solid. We will also encounter some kind of solid fluid operation, which involves filtration, sedimentation, centrifugation, flotation, and cyclone separators. So, moving onwards to the mechanical unit operation involving particulate solids. So, separation of the solid from the suspension through filtration process, then fractionation of the solids of white size wide distribution. Based on size distribution, we can do by gravity settling method or differential settling method. So, this kind of thing I am introducing on the first step, but in detail we'll be discussing in the later live sessions when we will be discussing the corresponding topics in detail. Separation of the immiscible liquids by centrifugation or decanting method, and then separation of the solids from the liquids by centrifugation. So, for handling of the particulate solids and understanding of the characteristics of the masses of particulate solids is very necessary in designing the process and also designing the equipments for dealing the different streams which contain such solids. So, as a chemical engineer point of view, we sometimes we need to design some equipments, or also in the mineral processing unit or in the any kind of chemical processing plant, we need to do all the mass balances. So, for that case, we need to analyze or characterize the masses of the particular solid that we are handling and their characteristics. This that means size, shape, any kind of other details like density, that can be bulk density or apparent density. Everything that matters for calculating the whole process flow sheet for the plant. So individual solid particle characteristics, those are characterized by basically size, shape, and density. So in this class, we'll be discussing one by one that how we are defining size for the bulk material or some kind of irregular shape particle, different kind of shape factors, and also how we are calculating the density. We'll be also doing some numericals in this class. I hope you people will be engaged more for solving those numericals. Uh, so moving onwards with the characterization of the solid particles. So we know that particles of a homogeneous solid, that means that all the characteristics are uniform um, over the mixture. So the particles in homogeneous solids have the same density as bulk material. We are assuming, but in real case, it is not always the true case. Well, when we do handling of bulk of material in the plant, suppose we are conveying through the conveying belt, the solids are being conveyed over the long distance to reach to the plant for the process plant at a particular processing equipment. Then through the distance or through the conveying of that bulk amount of the material, some particles may face some abrasion or some any kind of forces that may result in breaking the particles into or more smaller particle size, and maybe sometimes they may agglomerate or the particle characteristics may change over the conveying process. So that's what it is mentioned that particles obtained by breaking up of a composite solid, suppose any metal bearing ore, having various densities, usually they differ from the density of the bulk material. So when we are dealing with the bulk material and when we come down to the particle characteristics, these two cases are different from each other because we cannot assume in an idealized case that all the particles are in homogeneous conditions, and we cannot assume or idealize the case like the all the particles have the same characteristics like the bulk material. So in real case, it may vary. So we need to understand and we need to evaluate the actual case where the particles are being considered as a different, some breaking up solids or not a bulk in amount. As a particle, we can characterize those solids. So the size and shapes are easily specified for regular particles, such like a regular shape that we very much common to use, like a sphere or cubes. Those have some regular shape that we know, but there are some extraordinary, like irregular shape particle that we also generate throughout this conveying or the handling process. Uh, the terms and the term in terms of size and shape, those are not very clear, and those can be defined in a special way. So the selection of a relevant characteristics particle size to start any sort of analysis, that may be size analysis or density analysis or any kind of other measurement, they actually poses a great problem in the plant or in a larger view. When you are dealing in the industry, a lot of bulk solid you are dealing. So in practice, the particles forming a powder will rarely be spherical in shape. So uh, uh, often we idealize a particle shape to be spherical. But in reality, the shapes are not spherical every time. So they may be some kind of cuboidal shape, or there can be any kind of other shape like needle shape or any kind of flex kind of shape. It may be in the real form, but we oftenly it idealized as a spherical shape. So we cannot do that. We have to uh, be very stick to the point that if we are characterize one irregular shape particle in a certain way, we will um, we will characterize the other irregular shape particle through those means of characteristic size. So there are some definition of characteristic size. Those are especially dedicated to the irregular shape particle, that how we want to define it. So in many industrial powder form minerals, those are metallic or non-metallic in nature, they have been derived from very hard material by any sort of size reduction process. In such cases, the comminuted particles they resume some polyhedron shape, which has 4 to 7 faces and very sharp edges and corners. So this kind of real shape of particle, those cannot be idealized as a spherical shape. So we need to define a certain characteristic size or shape so that we can calculate their properties in a real case manner. So, the irregular shape particle can be described by a number of sizes. So, we will discuss one by one. There are definitely like three groups of definition for um, defining irregular shape particles. One is equivalent sphere diameter, one is equivalent circle diameter, and last one is the statistical diameter. So, at the first, we will be discussing the equivalent property of a sphere. So this system it denotes that volume diameter, sur- uh, surface diameter. This kind of different equivalent property of a diameter of a sphere is being defined. So in this group, what we are assuming that the diameters of a sphere, which would be the same property of the particle itself, are found. Like we are uh, idealize the case that the diameter of a sphere of the particle that having the property like the same volume as the particle having the same volume as the diameter of the sphere, like the sphere also having the same volume. So we will calculate the equivalent diameter out of that. So this kind of definition seems based on the equivalent property of a sphere. In the similar way, when we do the equivalent property of a circle, we calculate the projected area diameter. We will show a picture that will help you to understand that how that projected area diameter is being calculated. So this one is the statistical diameter that we mentioned. That is the ferrite diameter. I'll let you show the figure. Suppose this is a irregular shaped particle. This whole particle is irregular shaped particle. Now the ferrite diameter it calculates the tangent to tangent distance. Like the opposite to tangent, like this 2 point, you draw a tangent and the distance, the linear distance is measured as ferrite diameter for any kind of irregular shaped particle. For Martin's diameter, it just how it calculates the diameter, the linear dimension, it just bisect the image into two parts, and the linear dimension it is whatever it is measured, it is known as Martin diameter. Similarly, the shear diameter it is not shown here, but it is something that it refers to a optical microscope. This is microscopic analysis. So we will do whatever like two images in the microscope of the same particle will be done, and then and display so that they will be just touching, the images will be just touching, and the length of the displacement will be known as image shear diameter of the particle. So this is moreover microscopic study, and the maximum chord diameter, that is the maximum length of the line that covers the just like a straight line part, just like this maximum linear diameter. We can this two opposite line, we calculate the distance between two. Similarly, if we do this kind of line in the boundary, outside the boundary, that will be counted as minimum linear diameter. So any kind of irregular shape particle, we define this kind of diameter or this kind of definition of dimension measurement. So wherever it is applicable, we will follow the same rule for analysis the same sample. See, this one is the irregular shape particle. So at the opposite point, we are drawing the tangent and the linear dimension measured between the two tangents. It is ferrite diameter. The Martin diameter is the bisect the irregular shape particle. Where the spherical particle out of that, the projected area, that projected area, this linear dimension diameter is the diameter for this irregular shape particle. So these are some ways of defining the irregular shape particle because for a irregular shape particle, normally we cannot do the diameter analysis. So we need to do certain assumption for uh, either equivalence sphere method or equivalence circle, or either statistical this kind of method. So we will be moving towards the most important part, that is the sphericity. So the particle shape that we are going to deal with, we need to know the sphericity. Sphericity is defined. The shape of the individual particle is conveniently expressed in terms of the sphericity, which is obviously independent of particle size. That is very important to be remembered. For any kind of spherical particle of diameter dp, the sphericity becomes 1. Why it is 1? Because the definition says that sphericity is equal to surface area of a sphere with the same volume as the particle upon surface area of the particle. So the particle itself, if it is a sphere for special case, then sphericity becomes 1. So sphericity basically defined for the non-spherical particles, so that is sphericity always less than 1. So the surface, as you have understood, that the same volume particle we will take and we will equal it to the sphere of the to the volume of a sphere, and from there we will calculate the surface area based upon the equivalent diameter. That will be that way we can get the equivalent diameter based upon the sphere property. So this is another form of this sphericity. Um, and I will show you the derivation that how this formula comes. Let's take an so at first we discussed about the sphericity, that is the surface area of a sphere that has the same volume as particle upon surface area of the particle. So for a case, how do you define the volume for a sphere? PS suppose that is nothing but pi by 6 dp cube. And what is the surface area of a sphere? Denoting by AS, that is nothing but pi dp square. Now, by the definition, we are equating the volume of the particle equals to volume of the sphere. So what is the volume of the particle? Suppose Vp. And you know the volume of the sphere is pi by 6 dp cube. So from here, one derivation we can get, that is the dp, which is also known as equivalent diameter. This dp equals to, it comes 6 by pi vp to the power 1/3. Okay, so now from this equation 1, we can write that sphericity becomes surface area of the sphere having the same volume and surface area of the particle. Okay, let it denote that SP. So SP. So we don't know what is this value. So we can incorporate the volume here, like we made it from this derivation, we made it pi dp square is nothing but 6 Vp by dp. So from there we get sphericity equals to 6 Vp by dp into Sp. So this is the sphericity formula. The simpler this simplest form is mentioned in that slide, in that formula, and this one is the equivalent diameter for this case. So that's what the dp is the equivalent volume diameter of the particle, and Sp is the surface area of one particle, and Vp is the volume of that particle. For suppose for any kind of fine granular material, it is very difficult to determine the exact volume and the surface area of a particle. And for that case, the equivalent diameter dp is taken to be nominal size based upon the screen analysis or any kind of microscopic in examination. For many crushed material, the sphericity lies between zero point 0.6 to zero point 0.8, or particles, those are rounded by abrasion, the sphericity may be as high as 0.95. So sphericity of any particle which is other than a sphere, it is always less than 1. So we will move to the next first question of our session today, that you need to calculate the sphericity of a cylinder with a height equal to its diameter. That means for the cylinder, you consider the case L equals to D or L equals to 2R. So what will be the sphericity for this case? So I will give you a few minutes to think upon it and give me the answer. After that, we will quickly go through the calculation part for your easiest understanding. You just consider the part, simplest definition that we define for the sphericity. It will be easier to start with the basic derivation and come to the special case that I have defined here. So, for any kind of cylinder, you know, right, that volume defines by pi r square h, and in the surface area of the cylinder, it denotes like 2 pi r h plus the true circle, right? 2 pi r square. Now you, according to the definition of the sphericity, you equate the two volumes. Two volumes mean volume of the sphere and the volume of the cylinder. You equate these two and get the value of the equivalent diameter or equivalent radius. So in terms of the radius, the volume of the sphere to equate volume of the cylinder. That means 4 by 3 pi r cube in terms of radius, and for the cylinder it will be, we already calculated, pi r square h. So from there, r6. So from there you calculate the equivalent radius, which is nothing but 3 v6 by 4 pi 1/3. So you know the Vc value, 3 into Vc, that is pi I square is, it becomes 3. So up to this, it is, I hope it is clear. Then you will calculate the surface area of the sphere, uh, which is obviously you know that is 4 pi r s square. So from there we will calculate the sphericity, which is surface area of the sphere and surface area of the cylinder. So up to this, I hope it is clear. So we will now consider the special case where h equals to 2r. We will put simply in this equation. For this special case where h equals to 2r, we will calculate by last equation. We will put the value accordingly. And we will do some simplification of that equation. After the simplification, it comes around 2 by 3, 3 by 2. So this sphericity for the cylinder, it comes around 0.874. So I hope it is clear. If there is any question, you can ask that. I would love to give the explanation for that. If you have any question, I guess this is very simple derivation. In These are the step by step you can follow to calculate the sphericity of any kind of shape that has been given to you with a special case or any specification that we have mentioned for this case, that h equals to um, L equals to D or height, whatever it is. So we can derive step by step simple by following this rule of a sphericity, that surface area of a sphere that has the same volume as the particle upon surface area of the particle. So moving onwards, this is the question 2. Find the sphericity of the cuboid with dimension mentioned here. You calculate and let me know how you find out the sphericity value here. What should be the value? For the formula, the volume of a cuboid will be 10 into 5 into 3, 150 centimeter cube. And also the volume of a sphere is pi by 6 dp cube. So equate these two and let me know what is the dp you are getting. The dp will be, by equating, it will be 150 into 6 by pi to the power 130. The value, and what is the area of a cuboid? That is 2 into 10 into 5, 5 into 3, 3 into 10. What is the value? 190 centimeters square almost. And now you have to just calculate the sphericity. That is, I hope you got the same value. Sphericity of the cuboid for this dimension would be 0.7185. This value of the cuboid, it comes 0.7185, and we followed these simple equations step by step, and we equate these two volumes to get the equivalent diameter dp for the sphere, and we then followed the equation of sphericity, that is area of the sphere by uh, surface area of the particle. So we will move to the next topic, that is the surface shape factor. We will define the shape factor in two ways. That is the surface shape factor and another one is the volume shape factor. So how it is defined, the surface shape factor? The surface shape factor is a dimensionless parameter that compares the surface of a particle to that of a sphere having the same volume. So this surface shape factor is nothing but surface area of the particle by surface area of the sphere, which is exactly the opposite definition of the sphericity, right? So we can um, also say that surface shape factor equals to 1 by sphericity. For a sphere, surface shape factor is always 1 because these two terms becomes equal. And for the particles other than sphere shape, the surface shape factor is always greater than 1 because for any irregular shape particle or any shape other than sphere, the sphericity was less than 1. So for simultaneously, like for shape factor, the shape factor for those particles will be always greater than equals to 1. Now you define the volume shape factor, which is the volume shape factor. It is the ratio of the volume of the particle to the volume of the sphere having the same surface area as that of the particle. So that's why the simplified form of the volume shape factor is like this, and where the Vp is the volume of the particle and Ap is the surface area of the particle. So for calculating your shape factor, it is easiest way to calculate the shape factor that you first calculate the sphericity and then you just do 1 by sphericity, that will be the surface shape factor. And for the volume shape factor, you just have to calculate the particle surface area and then you can just follow the equation for calculating the volume shape factor. So it is easy to determine the mass of the particle accurately, but it is very difficult to evaluate their volume because they have irregular shapes and voids between them. When we deal with some porous material, suppose there will be voids and open pores or closed pores, so it will be very difficult for us to evaluate the volume, is accurate volume for the particle. So depending on how the total volume is measured, the different definitions of the particle density can be given. One is true particle density, one is apparent particle density, and another one is the effective or aerodynamic particle density. Coming to the first point, that is the true particle density, it represents the mass of the particle divided by its volume. This volume will exclude all kind of pores, pore volume. That may be open pore or closed pore. We have to exclude that from the total volume. And this density of the solid material of which the particle is made. It will denote the true particle density. Since the most inorganic materials consist of rigid particles, while the most organic substances are normally soft and porous particles, true density of many biological powdered material would be considerably low than that of mineral or metallic powder. When we follow the true particle density. Now you come to the apparent particle density. It is defined as the mass of the particle divided by the volume that will exclude only the open pores. And it is measured by simply gas or liquid displacement methods such as liquid or air picnometry method that is commonly used in the industry. The effective particle density, the last one, is referred as the mass of the particle divided by the volume that will include all the pore volume, open pore and closed pore volume. This density is of primary importance in the applications that involve flow around the particle like in the case of fluidization, sedimentation or flow through the packed beds. So, in the dimensionless form, we also introduce this term specific gravity, which is defined as the ratio of the density of the particle with respect to the density of the pure water. If is there any question till this part, you may feel free to ask. We will next onwards we will discuss specifically that how this liquid picnometry or the air picnometry process we follow to calculate the density of the particle. And next we will, at the last, we will um, do one question more based on the particle density. So how to do the liquid pictometry method? Here we can evaluate the apparent particle density and the true density. If the particles have no closed pores, this can be apparent particle density and true density can be measured by the liquid displacement. Now the liquid having high boiling point and does not dissolve the particle should be used in this investigation. So we use this equation for calculating the particle density through this liquid pictometry method, where we get the weight of the container that is filled of solid samples minus weight of the empty container. This mass into density uh, into density of the liquid that has been used, and this ml is the weight of the container that will filled with liquid only minus effective this mass, because m naught is the empty container weight and NaCl, which is denoting the container filled with both solid and liquid sample. So by this equation, we will able to calculate the apparent particle density or the true density. Based upon that, what is the condition of your sample? That is, you are considering the closed pore condition or what? Based upon that, you will calculate the particle density. Now, coming to the air pictometry method, you will get this kind of piston, two piston method. This in this form that this is the starting point. That at the start, the two pistons are at the same position. Now you put the powder and you press this. So the pistons moves in this direction. There will be pressure and this piston will move this direction. So, materials that are not surface active and incompressible in nature can be measured using room air conditions and following the standard procedure exposed to sample air pressure 1 to 2 bar. So, this piston will move this way and this reading will be captured here. So, the sample volume will be this much of displacement gap that will be denoted as volume in ml. So this is the method of air pictometry. We used normal air conditions and the sample should not react with the air, non-reactive. For calculating the effective particle density, we use the bed pressure drop method. So what is that? That the bed pressure drop method is based on the making measurements of the pressure drop as a function of the gas velocity u at two voidage conditions. One is the minimum and maximum voidage condition. So when the gas is passed through the bed of the powder in the laminar flow resin, the bed is first fluidized to get it well mixed and then it is allowed to gently settle to its maximum voidage condition, which, um, which is denoting as the case 1, and the bed is then tapped or vibrated slightly to reduce the void to a minimum value which is labeled as case 2. So in both the cases, we are going to measure the pressure drop in the bed, um, and this pressure drop calculation, pressure drop data is being collected for several range of gas velocities. So for each case, we are plotting the pressure drop versus gas velocity. So for that, we are getting the for Karman-Cozzeni equation, there is the linear relationship between pressure drop and the gas velocity. So from that, we get the linear plot slopes, that is S1 and S2 is mentioned. For case of maximum voidage, that will be S1, and for case of minimum voidage, that will be S2. So the equation becomes this, where the only unknown is the rho p is only unknown. We can get through the trial and error. In this, the we know the rho b that is the bed bulk density of the bed, because we know the volume of the bed, which is area into height. We know that uh, bulk density will be mass by bed volume, and also there is equation that is voidage is calculated 1 minus rho b by rho p. So from this we will get easily the rho v value. So the only unknown will be rho p. So by trial and error we will get to know what is the rho p value, or the density of the particle value. So coming to the next last question of this session, that is the you have to calculate the you have to calculate the true density, apparent density, and effective density of the particle, where we consider the porous spherical particle having mass of 15 gram, and its overall diameter is 2.5 centimeter, open pore volume is 2.5 centimeter cube, and closed pore volume is 1.2 centimeter cube. So you calculate this three density based upon this definition that we have discussed in the last slide. It will be very easy. You follow that the definition and you will be able to get. Again, I am mentioning the uh, volume of a sphere is pi by 6 d cube. So here the given data is dp equals to 2.5 centimeter. So the sphere volume is pi 2.5 cube by 6, which is coming around 8.17 centimeter cube. So the first step is calculating the true density. So the true density, it mass by volume. This volume will be total volume minus volume of the open pores plus volume of the closed pores. Mass is given. Total volume is 8.17 minus 2.5 plus 1.2. So the true density becomes 3.36 gram per centimeter cube. Similarly, the apparent density, it will be the mass and total volume minus total volume plus only the open pore volumes are included. So this one is the volume of the solid. And the last one is the effective density. So I hope this calculation is fine. Is easier to understand. That at first we will calculate the volume of the sphere, that will be the effective volume. But for calculating the true density, uh, we have to uh, we have to do minus of this open pore volume and the closed pore volume so that we get the true density. And for calculating the apparent density, we get the volume of the solid plus only the open pore, and the effective density we get the total volume 1.84. So for this lecture, this is up to this lecture we have discussed about the um, uh, different kind of possible um, uh, problems that we have solved. We tried to cover all of the equations and the useful equations through the numericals. I hope this numerical will solve you to complete your assignments for this week one. And I covered the basic knowledge also regarding the shape and size and how we calculate the experimental method as well for the density of for density evaluation of the particles. If is there any question you would like to ask, and you can also post your question regarding any kind of concern for this week one content in the question and answer this portal in the NPTEL website. And in the next session, we will be covering the size analysis. We will be doing the screening, different kind of diameter that will be defining, and the screening analysis and cumulative analysis and those kind of